I'm Soham,
I'm David.
and today we're going to be talking about IVT, MVT, and Rolle's theorem.
Okay, so the very first thing that we have to do to understand these things is understand two terms, continuous and differentiable. These are both crucial pieces to understanding IVT, MVT, and Rolle's theorem. So what exactly does continuous mean?
It's continuous.
What does that mean?
So there is nothing on the graph. That is not a good definition.
Okay, here, draw a graph.
I can draw it.
Draw a graph here.
I can draw it.
Let me get the green color. Green. Is that the right green?
It's a good green.
Okay, so draw a graph that would be continuous.
So if this is the coordinate plane. That's a continuous graph.
On the interval where the endpoints are, right?
Yeah.
So basically when something is continuous, it means that there is no hole, there's no jump, and there's no asymptote that is disrupting the graph.
Yeah, so here's a graph that is not continuous. That's not a continuous graph.
Because there's a vertical asymptote right here. So that would not be continuous. In order to use all three of these ideas, your graphs have to all be continuous.
Yeah.
And then differentiable is a little bit different.
So we know some things that are not differentiable. For example, an absolute value function. And the reason it's not differentiable is because the slopes on either side of this point right over here,
zero,
are different.
X equals 0.
X equals 0.
Yeah.
They're different slopes, so it's not differentiable. If you have two different slopes on either side, it doesn't work.
So think about this. If you have like an absolute value thing, this point is not differentiable because like what would the tangent line look like for this? It could be here, it could be here, it could be here. It's not differentiable because there are multiple infinite amounts of tangent lines that could go there. So it's not differentiable. Other things that are not differentiable are like cusps that look like this. That was a really bad cusp. So it's like a little, I don't know how to explain that.
A cusp.
Yeah, a cusp. Like a little spike thing. Yeah.
Because it, again, could be in an infinite amount of places.
Yeah, so it could be here, it could be here, it could be here. It really, I don't know.
Another thing, so the reason it's not, like this function, like a negative x squared, that's differentiable because it's only one place it could be, which is up there. With a cusp and an absolute value function, because of the slopes are different on either side, it could be an indeterminate amount.
And when you say they're different on either side, this slope, is this pointer working? Yeah. This slope is like positive and this is negative. They're like totally different things. So that would not work.
Yeah.
Okay, so now let's jump into the actual topic of this video. So the first thing is Intermediate Value Theorem.
It's very easy.
This is like kind of newer for us, but it's really simple actually. So let's get our blue. So basically what IVT says is if you have a graph between, let's call this, that's a really bad point. Let's call this like x1 and x2, right? And there's this random graph that looks like that, right?
Sure.
Yeah. So all this is saying is that if this function is continuous,
it does not have to be differentiable, just continuous.
It doesn't have to be differentiable, just continuous. That means that, let me think what I'm trying to say here. So
there is a point, x sub 3, let's call it, that exists. Specifically, let's say this function is f of x.
That's a horrible line, whatever.
This function is called f of x. So between f of x sub 1 and between x sub 1 and between x sub 2, there is a point, f of x sub 3, which is there.
Okay, this is really confusing in this way. Let me try and explain it a different way.
You should draw a linear function and just...
This is fine. This will work. Okay, so let's say that this coordinate right here is... I'm going to actually switch colors back to green. Let's say that this coordinate here is like, I don't know, 5, 2, right? Just random point. And let's say that this point over here is 7, 4. All IVT tells you is that there has to be some point within this interval that has values, y values, between 3 and 4. So that means that because this function is continuous and it gets from y equals 2 to y equals 4, there has to be a point that equals y equals 3, or something in there that, like, all values between 2 and 4, right? So, like, this point right here, is in between 2 and 4 somewhere. IVT just guarantees that. This is really helpful in problems where they give you like charts of values because it can help you guarantee that certain points exist.
Yeah. On a linear function, which is more easy to think about because it's more simple, let's say this is just y equals x. Between x equals 0 and x equals 1, there is a point. But so, because this function is x equals y, so between 1 and 2 for x or y, they're the same thing. Because x equals y. There's a point that exists 1.5.
Yeah. So IVT is just guaranteeing that. So if this is like 0, 0, and this is like 1, 0, 1, 1,
1, 0.
1, 0, then there has to be a point in a y value in between here that's 1 or
1 half. 1 half, yeah. Because it's continuous. It has to pass through every value.
In order to get to the second y value, it has to. Otherwise, it wouldn't be continuous. If there's a hole, then it's not continuous. So that's basically IVT. It's really easy to understand. It can be used as justification for a lot of things on the AP test, and just kind of if you think about this concept and like you didn't really know how to explain it, this is how you explain it. You just IVT, and that's a good justification for a bunch of things. So let's go on to MVT. Okay, MVT we've already gone over a few times. It's pretty easy to understand also. So basically how MVT works is if you have two points, let's say, I don't know, let's say you have a random function that looks like this. Again, a weird function. And you have these 2 points. Let's call this x, comma, f of x. And, or that's bad, whatever.
Thanks.
And we'll call this b, comma, f of b. Actually, that's wrong. It should be x also, because it's on the same graph.
No, because you're saying evaluated at point B.
Well, it would be... whatever. Fine. Fine. It doesn't matter.
X and Y.
So, all this is saying is that if you find the average rate of change between these points, which is delta y over delta x...
otherwise known as the secant line.
The secant line.
So...
well, yeah. Would be like...
f of b minus f of a over b minus a.
It's x. I made it x, but whatever. It doesn't matter. Over b minus x, right? That would give you a secant line. It would give you a slope that looks a little bit like this, right? That would be the secant line.
The slope of the secant line would look like that.
Well, that is what the secant line looks like.
Well,
doesn't matter.
It also is the slope.
So all this is saying is that there has to be a point if this function is continuous and differentiable. We went over what those mean. This function is continuous and differentiable. There isn't an absolute value. There isn't a hole. It's continuous on every point because there's no like disruption.
Oh, important to note. It has to be continuous and differentiable on the interval. So if this graph had something weird going on, I'll draw this in yellow just to show that it's not part of the interval. So like over here, there's an asymptote and it does this. That doesn't matter for us because we're concerned about this interval from x to b.
Yeah, so if the whole function and it's only asking about a certain interval, then that is still continuous.
Exactly.
And so all MVT is really saying is that there is a slope on this interval that is the exact same slope as the secant line between two different points.
Not a slope, it's the slope of the tangent line.
It doesn't matter.
It matters.
It doesn't matter.
It's not a linear function, so it doesn't have a slope.
Whatever. There is a point that also has a tangent line with a slope that is the same as the secant line of these 2 points.
Yes, there is a point, f prime of c, that was a bad c, which equals delta y over delta x.
Yeah.
That was...
Thanks for writing on the title.
Let's not do that, maybe.
Okay, just don't even write that. Just get rid of it.
But there is a point f prime of c that equals delta y over delta x.
So, I don't know where that would be. Maybe like here-ish. Let me do blue again. It's kind of like a similar slope there, right? Similar
Slope of the really tangent close. Line.
Shut up.
It does not have a slope.
See, this is also kind of the same. Yeah, so MVT just guarantees that there's a point in there that is the same thing.
Yes.
Okay, so that's pretty...
self-explanatory. Not self-explanatory.
Not self-explanatory.
But we explained it.
Okay, so now let's go to the next one. Fair?
Yes.
Okay, here we go.
Rolle's theorem?
Rolle's theorem is
Similar.
it's basically MVT except for a very specific instance. It's saying that if f of b, I should not be in blue. If f of b
Use A this time.
equals f of a, then there has to be a point on the interval where the slope of the tangent line is 0. Now, this has to be continuous and differentiable again.
On the interval.
On the interval. So I'm going to draw another graph, yet another one. Except this time, the points are going to be on the same y value. So I'm going to go like this, right?
Yeah, that's fine.
So we're going to call this f of b right here.
It's like a lopsided
I don't know why I'm
sign.
doing f of b first. It doesn't matter.
Weird.
Okay, so these points are equal. They're on the same axis, right?
Yeah,
That was a really bad axis.
the y values are equal.
All that means is that in this interval, there has to be a point
Where the tangent line slope is 0.
0, because...
So where the derivative is 0.
And how this relates to MVT, really, is that the slope of the secant line between these 2 points is 0. So, I mean, delta y over delta x is 0.
Yeah.
So it's just applying MVT to a very specific situation. So in this case, you would have a slope of 0 here, you'd have a slope of 0 here, you have a slope of 0 here. It just guarantees that there is some point. It has to be continuous and differentiable. If it's not, then that would not work. If there was, I mean, it could work, but it wouldn't. It's not like something that you can guarantee.
Yeah.
I mean, if there was
You might get lucky, but
if there was like a
not
hole
allowed.
here and like a hole here or an asymptote here, then like you wouldn't have any slopes of 0. Also here. So that's how that works.
Another thing, you might be asking, what if the line is just not x, but y equals 2 or something? Well, because f of b and f of a are still equal on like every point here.
And
Well,
it's continuous and differentiable.
it still works because there is a point on that graph where y prime equals 0 every point, because if you draw the tangent line anywhere, we'll draw that in blue.
Yeah, we get it.
It's 0.
That's not the tangent line of what that looks like, but whatever.
It's a bit closer. It's less sloped, more 0.
Is it true that like endpoints don't really apply to this? I don't know. Yeah, endpoints don't apply to this.
What do you mean by that?
Like endpoints cannot be cannot be the c value that has the tangent line of that, obviously.
I mean, in this case it does.
Well, you can't have a tangent line of an endpoint.
You're right, because it doesn't have a slope on the other side.
I mean, yeah, it would just be like
At least
here,
I think that's
random.
the case.
I'm pretty sure that's how it works. You can't use an endpoint as like one of the points that you're trying to prove with Rolle's theorem or anything. Okay, so is that it?
Yeah, that's Rolle's theorem, which is
Okay.
just a derivative.
That doesn't make any sense. A derivative of MVT?
Yeah.
You're stupid.
Not
Okay.
a derivative as in a math derivative, but a derivative as in
Okay,
an
we're
English
done
word.
with this. Okay, so yeah, that's it. Goodbye.
Thanks for watching.